Muy buenas tardes. El Grupo de Estudio y Trabajo en Cannabis de la Facultad de Agronomía de la Universidad de Buenos Aires les da la bienvenida a este nuevo seminario, después de algún tiempito. En este caso, el título de nuestro encuentro será Avances en Biología de Sistemas de Cannabis Medicinal. Y para este encuentro tenemos a quizás la máxima autoridad mundial en el tema. Estamos hablando del doctor Germán Spangenberg. El doctor Germán Spangenberg nació en la República Oriental del Uruguay. Luego de completar su maestría en Ciencias Agrarias en la Universidad de la República en ese país y su doctorado en la Universidad de Heidelberg y el Instituto Max Planck de Biología Celular en Heidelberg, Alemania, realizó investigación postdoctoral en este último y en el Instituto Federal de Tecnología de Suiza, conocido como ETH por sus siglas en alemán. Cito, en Zurich, Suiza. Allí se desempeñó como profesor asistente y profesor asociado y obtuvo su título de doctor en ciencias en agrobiotecnología. Luego se trasladó a Melbourne, Australia, donde ingresó en el Servicio Agrícola del Estado de Victoria, conocido como Agriculture Victoria. Allí fue director del Centro de Biotecnología Vegetal, director de investigación en genética y genómica vegetal y director ejecutivo de investigación en biociencias. Además, se desempeñó como investigador principal en centros de investigación de primerísima línea de Australia del ámbito privado. Actualmente, el Dr. Spangenberg es director de investigación del Servicio Agrícola de Victoria. En la Universidad de la Trobe es profesor de genética y genómica vegetal, así como director de la Escuela de Biología de Sistemas aplicada. A su vez, es director de AgriBio, Centro de AgriBioscience, una iniciativa conjunta del Servicio Agrícola de Victoria y la Universidad de la Trobe. También es director y director científico de Phytogen Pty Limited, empresa dedicada a la biotecnología agrícola. En 2006 recibió el premio al Pensador Australiano del Año. En 2007 fue electo miembro de la Academia Australiana de Ciencias Tecnológicas e Ingeniería. Ha sido presidente de la Asociación Internacional de Biotecnología Vegetal. En el Día de Australia de 2017, el Dr. Spangenberg fue galardonado con la Medalla al Servicio Público por su destacada labor pública en los programas de investigación científica para el sector agrícola en el estado de Victoria. Luego de esta bastante larga introducción, que seguramente es nada más que un apretadísimo resumen de la trayectoria del Dr. Spangenberg, los dejo con él y su presentación. Hasta luego.
Muchas gracias a Cecilia y muchas gracias a todas y todos por participar en este seminario hoy. Espero que me escuchen bien y que vean mi screen. Voy a pasar ahora a hacer la charlita en inglés y luego al final hacemos las preguntas y respuestas en español. Perdón por ese cambio de idioma. The topic that I would like to cover today basically covers four areas. I'd like to go through an introduction, then to share with you the journey of enabling and establishing a medicinal cannabis industry in Victoria and in Australia. That would be approximately half of the seminar, and the second half I would like to go more into technical details covering our work in plant systems biology, very much from genome to phenome, and then finishing with some summary and conclusion. So that's a bit of a plan for the next hour or so. As you well know, cannabis, this wonderful plant has had a very long history of safe use for medical applications, and approximately around more than 5,000 years. The first reports are in 2737 BC, and in China, and I think is the first recorded use of cannabis as medicine reported by Genome. In 200 BC, Huatuo is part of the Han Dynasty. Reports and the first use of cannabis as anesthetic for surgery that were actually really rough surgical treatments at the time. And then it found its way, its use in medical applications of cannabis in the Western world. In 150 BC, Galen, the Greek physician, was first to prescribe cannabis for a diversity of medical conditions. In 1563, Garcia da Horta, the Portuguese physician, was the first actually to report medicinal effects. So trying to understand not only the application fields for cannabis for treating medical conditions. And it took a couple of further centuries until William O'Shaughnessy, an Irish physician in 1842, actually started the first clinical trials in a sense and demonstrated unequivocal the applications of a medicinal cannabis as not only as an analgesic but also as an anticonvulsive, and setting actually the basis ultimately for treatment of a use of cannabis for treating epilepsy. And it is well known in the 1850s, Queen Victoria, who suffered horribly of a premenstrual syndrome, that she was receiving on a regular basis cannabis for PMS treatment. So a long journey of 5,000 years through the ages of safe use of cannabis for medical applications. Now then we went into a period of time and where cannabis, more because of its psychotropic features, was considered was a prohibited drug, and that happened through to 1992. When we see for the first time in Israel the legalization of medicinal cannabis. And that took off multiple jurisdictions through to more recent times, and a patchy landscape initially in the US with California on a state-by-state basis. Chile, the first country in South America, then to legalize it in 2005. And Uruguay in 2013, and in Argentina and in Australia in 2016. So that's to go through quickly through a bit of the journey of a safe use of cannabis for treating medical conditions, the path of the period of prohibition, and then a path now to seeing it legalized across multiple jurisdictions across the world. So what I want to do is to tell you how we approached this legislative reform on the one side, and the task that we took in Agriculture Victoria to pave the way as government to the use of medicinal cannabis with also a strong sense of building and supporting that emerging industry. So in 2014, the Labour government of the time had as an election commitment to seek advice on the mechanism to provide legal access to medicinal cannabis in Victoria. In 2015, the Victorian Law Reform Commission report was tabled and informed the development of an Act of Parliament. The Act is called the Access to Medicinal Cannabis Act, that was introduced to Parliament. And in 2016, that Access to Medicinal Cannabis Act was enacted, and that was through basically a legislative reform driven by the state of Victoria in Australia, and shortly that followed by changes in both in policy and as well as legislative changes at the level of the federal government of the Commonwealth that said then up a very comprehensive Commonwealth regulation of cultivation and manufacturing. And importantly, also changed the scheduling of medicinal cannabis products under the poison standards to facilitate medicinal access. And so that meant that development in Victoria, and that's one of the tasks that I got in my role at the time, is to set up basically the science base and the capability in the state. And we supported and also shared our experiences with the federal government in order to pave the way for the changes both in policy and legislative changes at the Commonwealth level. In November 2016, imported medicinal cannabis became legally available. In 2017, actually bulk imports of medicinal cannabis products were permitted. And in 2018, also the export of medicinal cannabis products was permitted. So I'll go through a bit more detail on how we approach in Victoria, leading in a sense the Australia's regulatory reform as well as the development of this industry. On the 6th of October in 2015, as I mentioned, the government announced its policy approach for the Victorian medicinal cannabis scheme, and that was for patients in exceptional circumstances. And the primary target group of medical conditions were kids, were children with intractable epilepsy. And in a bill basically to operationalize the access to medicinal cannabis was introduced to Parliament on the 8th of December 2015 and passed on the 12th of April of 2016. And the role as head of Agriculture Victoria Research at that time that I took was basically to implement that medicinal cannabis policy as approved by the Victorian Cabinet at the time, and basically covering three phases. The first phase was to undertake a horticulture cultivation research trial, so to get the experience in order to be able then to support the phase two. There was, as government, to undertake cannabis cultivation and extraction for an initial cohort of patients that, as I indicated, the target group were children with intractable epilepsy. And then morphing as a path was technically, scientifically, and regulatory de-risked, and shifting the role to one of supporting the development of the medicinal cannabis industry. And that obviously includes a research as well as the provision of technical services. So that was the third phase, and an ongoing role in doing so. And so that was a bit of the journey that we undertook. Now, to put a bit of the framework or the context that we needed to operate at the time, and this was just the state of Victoria initially, and in setting up the basis for the industry, that is needless to stress a very broad applicable legislative framework, and there are a series of international treaties that Australia is party to. There is Commonwealth or federal government legislation in Australia as well as Victorian legislation, and the international treaties, as you are aware, there is the United Nations Single Convention on Narcotic Drugs, there is the Convention on Psychotropic Substances, and is the Convention against the illicit traffic in narcotic dangerous psychotropic substances. At the federal government level, there is the Narcotic Drugs Act, the Customs Act, the Crimes Act related to the traffic in narcotic drugs and psychotropic substances, the Quarantine Act, and also the Therapeutic Goods Act. And at a state level, there is obviously the Act of Parliament related to drugs and poisons and controlled substances, as well as the Victorian State-Based Therapeutic Goods Act. So a complex legislative framework that we need to operate at the to start the development of the industry. So it took us some months and to put in place all the approvals in the compliance management framework. There was compliance approvals from Victoria Police, from the Department of Health and Human Services, from the Department of Economic Development, and also from these are state-based regulators and government departments, and the Therapeutic Goods Administration with its Office of Drug Control and the federal government. And importantly also to note that cannabis is considered a weed in Australia, so requirements of securing all the compliance approvals from the Department of the federal government Department of Agriculture, Water, Resources. And the federal government had under the Therapeutic Goods Administration and the Office of Drug Control, the requirement to license to import, a series of licenses and material transfer agreements related to germplasm, import permits related to germplasm, and export permits related to germplasm, and to do all of that compliance with the obligations that we had that Australia has as party to those international treaties that I mentioned earlier. So the next step was, and there's I'm briefly outlining the journey from 2000 and while informing the policy positions and informing the legislation, but also then building all the capability in the state to for a new, safe, compliant, science-based emerging industry. So we established Australia's first cultivation facility. We established Australia's first manufacturing facility. We'll go through a bit more detail about that in a minute. And this is an image of Daniel Andrews, who is the Victorian Premier that provided significant government leadership for this process. That also implied to develop quality systems and standards, and so we secured Australia's first good manufacturing certification, and so or GMP for short, and develop all the quality systems and GMP process, all of that underpinned by our research capability and science expertise and infrastructure in agricultural editorial research. And importantly was also ensuring that we can safely demonstrate full compliance with the legislative framework, and in the form of being able to identify in all the tracking and tracing of from every single seed, propagule, cutting, plant, and milligram of cannabis biomass through to a extracted and manufactured cannabis products. With a period of time, we bred over 275 proprietary strains, and I will go through this a bit more detail later. And importantly, also we wanted to inform and support the path for registration of varieties and or strains. So we tested the working with IP Australia and secured Australia's first plant breeders' rights for medicinal cannabis, noting that it's a highly regulated crop. One of the key elements, as I indicated, was to be able to demonstrate that full compliance in an auditable manner and meeting all the requirements ranging from Victoria Police through to regulators at the state and at the Commonwealth level and the Office of Drug Control is all the identification, tracking and tracing systems. And so we develop all the IT database and systems, and that allow us then basically to track and trace from seed packets, every individual seed, plants, propagules, mature plants, and dry biomass batches. And each of those then issued with a unique identifier, barcoded, and all the information connected to each barcode is then captured in what we call a biological tracking sheet database, so fully auditable, and building the system that also allow us ultimately to support the development of the industry. And so I'll give you a bit of an example that we can also link biological materials all across the continuum of genetic improvement through to every the outcome of every plant. And if once we make a selection and we decide to discontinue with the material, so that we have full accountability and plants from also including all the work that we do in vitro culture, and I will describe some of that later. And so is to the capability and services to industry related to cultivation and production. And actually we grow the cannabis plants using exclusively in indoors cultivation system, and with hydroponics on coconut substrate tubes, as the ones that you see here in the image, and then having them cloned, so vegetatively propagated plantlets that from the chosen strains that we breed are then transplanted into the hydroponic system setup, and on indoors cultivation facility benches. And the plants are grown initially vegetatively until a desired biomass status is reached, and then are transferred to a bloom room, shifting photoperiod conditions in order to enable flowering induction and the production of floral buds that obviously is the target primary harvest organ. And so one of the services that were provided to set up the industry was the provision not only of licensing of strains that we breed, but also maintaining strain services to industry once industry built the respective larger commercial scale cultivation facilities. And that was, in a sense, a summary of the phase one, and that horticultural research trial to set the basis and to inform and support the industry. The phase two, at the time, got the task to do a routine cultivation over a period of time in order to be able to manufacture medicinal cannabis products. So so not only growing biomass, but processing and storing that biomass. And as you know, the whole plants are harvested, processed for drying under a controlled environment, and then the dried whole plant biomass is ground using a grinder, like you see here on the left image. And you see here the ground biomass. Sorry. looks like yerba mate, and with a 2 to 4 millimeters of size, a particle size, and then that grown biomass is packaged into plastic containers for storage, and we build a environmentally acclimated and so air-conditioned, very large vault that allow us then to securely store that biomass. And so these are images on the right side here of that purpose-built vault. And so another element that we did to support the development of the industry in its transition phase is the provision of biomass processing and storage services to the industry. So when industry was able to do cultivation, but didn't have the ability to process that biomass to be able to support them in doing so. The next stage was basically to build all the capability and enable services to industry for the manufacture. So this we constructed in Australia's first extraction and manufacture facility for the manufacture of medicinal and cannabis, and we procured imported an extraction equipment that we installed here. You see the image on the left side. But then we developed and we built and designed a custom solutions for the extraction of biomass. So what you see here in the right image was add-ons that we built and designed and fabricated and installed. And the decision that we made at the time in order to be able to manufacture medicinal cannabis for a range of patient groups, including being responsive to, for example, halal and in other religious perspectives. We decided not to use alcohol or any organic solvent in the extraction, and so we focus on supercritical CO2 extraction and being in that way, on the one side, fully compliant with the Office of Drug Control, with the Therapeutic Goods Administration, as well as a workplace safety, occupational health and safety requirements being met, noting that we're dealing with in a very highly regulated, a regularly secure operating environment, but using supercritical CO2 extraction with very high pressures. So that enabled us then to, as I indicated, to secure Australia's first GMP good manufacturing practice from the Therapeutic Goods Administration, and setting the basis for being able to also provide GMP accredited extraction and manufacture services to industry. So that was setting basically the basis for the phase two, and furthermore, we've in order to secure also the GMP certification, we developed all the standard operating procedures. So we have a suite of GMP documents that are required that provides all the evidence for the quality assurance, the quality control, and the manufacturing. So a totality of over 200 documents were generated, and importantly, doing all the very comprehensive staff training implemented in the form of ensuring that those standard operating procedures are strictly implemented and adhered to. And again, that another element that we did is the provision of those standard operating procedures, as well as advisory services to industry to enable, as market failure disappeared, as industry could embrace roles that initially we did as government, and to pave the way for a strong, high-quality, pharma standard, fully compliant science-based medicinal cannabis industry. So that was the completion of setting all the basis for the phase 2, again from breeding strains and of cannabis, doing all the cultivation, all the steps of the process through to certificate of analysis with the manufacture of medicinal cannabis products to support access to patients as well as to clinical trials. Another critical part was the role that we played was obviously engaging with government and industry stakeholders. As I indicated, is Daniel Andrews, our Victorian Premier. Is a former Minister for Agriculture in the state of Victoria, Jella Pulford, another Minister for Agriculture in the state of Victoria, Jacqueline Symes, and then sharing the experience that we gained in Victoria with other jurisdictions, with other states and territories. So these are the corresponding heads of the agriculture departments across the country, covering from Western Australia, South Australia, down through to Northern Territories. And in cannabis strains that we bred and all the expertise that we gained, also we licensed and transferred to industry to empower the private sector to take over roles that initially we did as government in cultivating medicinal cannabis and in manufacturing medicinal cannabis for a cohort of patients, but always the intention was not for government to have an ongoing role in that, but rather reverting to our critical role of doing research and quality science, and letting then ultimately industry to be able to commercial produce and manufacture medicinal cannabis. A critical part was also to contribute to the development of the knowledge workforce for the industry, not only for us to be able, as Agriculture Victoria Research, to be able to undertake this work, and but also training staff and students to build the knowledge workforce also for the industry moving forward. And here you see a couple of images of recognitions of the awards and along the way in the team in Agriculture Victoria Research and students that we trained from the policy legislative framework through to manufacture and cultivation. Now, another important aspect was to set the instruments, let's say the intellectual property assets required to enable value capture and to support industry moving forward. And so we developed and registered a range of intellectual property assets. As I mentioned, we wanted to pave the way for the first time for the registration of breeders' rights related to novel strain genetics, and that approach was established for hemp, but not for medicinal cannabis, and obviously the experimental designs and the approach to provide the evidence to support the registration needed to be developed and tested, and also we filed a range of patent applications for all the technologies and know-how that we developed along the way, and which would be, I will describe those technologies and tools in the second part of this seminar in a minute. But I think an important part, including also registering the AgriBio as the trademark and for our proprietary genetics. A few words on the path of developing the industry. And so we had what we called an industry development plan. And as I indicated, the journey from 2014 through to 2018, a 5-year initial cycle covering the elements of the legislative reform, informing that the corresponding legislative changes, as I indicated, securing the first authorizations in Australia from the Office of Drug Control as government to be able to cultivate medicinal cannabis and manufacture it, and then facilitating, as indicated, medicinal cannabis plants that we bred and cultivated, and ultimately transferring those to Victorian commercial entities to be able to do that activities moving forward with the intent of building an industry that is exclusively and strongly science-based, with pharma quality standards, and in position to realize opportunities not only for the domestic market, but also from export market. And then we developed, after that first accompanying that process in setting up the industry, a second phase of that industry development plan from period 2018 to 2021. These documents are publicly available that illustrate the path and the approach that we use in Victoria for it. The key elements then of moving forward was obviously developing new innovations and doing the routing by partnering. We do it via our commercial unit or within Agriculture Victoria, that is called Agriculture Victoria Services, which is co-located with Agriculture Victoria Research in our major research facility based in AgriBio on the campus of Trobe University. And so in the key innovations of the routing by partnering then relates to novel and designer strains. I will tell a little bit more about that. For medicinal cannabis, a range of active innovations. We develop also microbiome products for medicinal cannabis that I won't cover today, and then the provision of technical services, collaborative research and development, in strains, licensing by Agriculture Victoria Services, our Bio strains for the industry to be able to cultivate, to grow. And the provision also of GMP, a manufacturer technical services, again addressing market failure, noting that the industry development started first with the ability of commercial entities to cultivate, but as they progress through stages, required a GMP manufacturer technical services. And then ultimately, as we do for all our target crops, establishing and positioning a platform for genetic innovation. And in this particular case, we branded that and we call it AgriBio, and for specifically for cannabis and for pharma and wellness application. So summarizing the first half of what I wanted to share with you today, there was the journey of those three phases that I indicated. Starting point was securing and obtaining all the federal, state, and international regulatory approvals and permits. Then obviously sourced legally and seeds that was starting material, and I will describe the G.E.T diversity and the path that we use for breeding proprietary strains. The seeds were germinated, the plants were DNA typed, were chemotyped, and so the morphotype evaluated. Then we bred a large range of strains covering every possible desired chemotype profiles. We evaluated the propagation characteristics of the strains. We sequenced the genomes of all of them, and we established facilities for is Australia's first for medicinal cannabis production and extraction. We secured the cultivation authorization by the Office of Drug Control from the Commonwealth, from the federal government. We obtained the authorization for, is in Australia first, for the extraction and manufacture of medicinal cannabis by the Office of Drug Control. And we obtained from the Therapeutic Goods Administration, Australia's first good manufacturing practice license for the manufacture of medicinal cannabis products. And then we undertook over a 12 months period, basically, whilst industry was building its own capabilities for cultivation. Basically, we did weekly production of medicinal cannabis resin for product formulation, for supply to patients and to clinical trials from biomass that we cultivated through to June 2018, completed that first phase of the industry development plan as government. And as I indicated, we developed a wide range of intellectual property assets, providing technical services and licensing of that intellectual property assets to industry, and undertaken in industry development in order to enable the industry to ultimately undertake commercial cultivation, extraction, and manufacture of medicinal cannabis biomass cultivated by industry from July 2019 onwards. And so that the transition 40, or what we call the phase 3, that has basically has an ongoing role, a focus on research and building on our expertise in plant systems biology, very much from genome to phenome, which that gets me back to the title of my seminar today. But I thought it was important maybe to share with you the journey that we had behind the science that I will describe now in the second part of my seminar. So when I make reference to systems biology, largely what I mean is a large-scale, high-throughput approaches to characterize a biological system. And again, from genome through to transcriptome, metabolome, volatilome, proteome, and ultimately the phenome. So industrial scale approaches or contemporary approaches to a biological, a comprehensive description in an integrative manner of biological systems, and that's the spirit of the approach that we use throughout all our target crops and in agricultural Victoria research and other activities. Cannabis was the logical one. Is a new industry we wanted to build to focus our efforts. Now, one of the implications of that long period of time of prohibition and means that cannabis lacked the knowledge base and data sets and information and so on. So by prohibiting something, then obviously one limits the ability to generate knowledge. So there was, in a sense, is the key strategic opportunity for us was to address the paucity in application of contemporary agribioscience to medicinal cannabis. And this gives a sense of a core set of capabilities that we have in our main research facility in AgriBio, but also in our key regional sites in Victoria, using that expertise and skill base applied in a highly focused manner into medicinal cannabis with intention of enhancing the knowledge base in a global context for supporting the development of this industry moving forward. So we'll shift now gear and we'll focus more on some of the science and behind our work in cannabis, and starting first with some of the complexities in cannabis taxonomy, and I think I would possibly refer to it more classification than taxonomy. And obviously, cannabis is the name of the genus, is the family of the Cannabiceae, and that describes or reported three subspecies. So of the species Cannabis sativa, the subspecies are Sativa indica and ruderalis, and which changes or primarily differences in two dimensions, and one is in part of the morphotype, and also a chemotype from a perspective of the two major cannabinoids, the psychoactive tetrahydrocannabinol, or THC for short, and the non-psychoactive cannabidiol, or CBD for short. And one of the key phenotypic features that is used also complementing that is the width of the shape of leaves. And but I think it's important to recognize that we should actually refer to as one and a single species that is called Cannabis sativa. Another implication of the long period of prohibition is that we'll see a range of street varieties with some funky names, but biologically those names mean actually nothing, and possibly under the same street variety name, there are very different genetics and chemotypes, which makes particularly pressing the need of really bringing science behind a varietal development that has taken place over a long period of time in an illegal manner. Now, I will take you now through a journey genuinely from genome to phenome, and so setting a bit the basis for that. So as I indicated, there are three subspecies of Cannabis sativa that are called Sativa indica ruderalis. It is in erect, is an annual, and is a dioecious, herbaceous plant. Has a diploid genome of 20, so that comprises 9 autosomes, and has a pair of 6 chromosomes, so a 6 determination system with an X and Y chromosome, not dissimilar to humans. And the female plants are homogametic with a XX, a sex chromosomal composition, and the male plants are heterogametic with an X and Y chromosomal setup. And the haplogenome is 818 megabase pairs, and we'll come to that a bit later in the female plant, and has the Y chromosome is a large chromosome, so the male plant will have a haplogenome size of 843 megabase pairs. The intention for us for doing science in medicinal cannabis systems biology was to set the basis for precision breeding in medicinal cannabis, and the starting point, as a consequence of the prohibition that I mentioned, is that there was very few draft genome sequences were available when we started our work. The male Y chromosome was still sequenced uncharacterized. The genes for cannabinoid biosynthesis were very poorly functionally characterized, and there was very limited characterization of the pangenome, transcriptome, metabolome, and proteome and phenome levels. So you would do a literature review, we'll see that when we started our work, there was not much there. There was also very limited availability and in application of contemporary molecular breeding technologies and tools. So there was a very large scope for improvements. And on the other side, there were many breeding targets that required attention from yield through to disease resistance, needless to stress the chemical compositions and many others. And so the paucity in the application of contemporary biology approaches to study cannabis was very obvious at the time. And for us, it was a strategic opportunity for the Australian medicinal cannabis industry that we felt that it could greatly benefit from advances in plant systems biology. And okay, so very quick, I think I covered that in detail. So we shifted all the first cultivation facility, the manufacturing facility, and GMP manufacture from a path of a developing products for patients in clinical trials and into supporting research and innovation. And with the intention of setting the basis for a medicinal cannabis industry that is strictly underpinned by advances in plant systems biology and strictly focus on the highest possible standards, pharma-like standards. And noting that is critical and essential to provide them confidence to prescribing GPs to ultimately realize the public health outcomes that we wanted to pursue from the changes, the legislative changes that we undertook in the path from 2014 through to 2016. So we'll go through now focusing on how we went about breeding strains. And so we bred, as I indicated, over 275 proprietary strains and securing through to the first plant breeders' rights, which was obviously a continuum that was important. And the starting point was to establish a globally very diverse reference population in order to enable us to do genomic-assisted strain development. And these are the stages in the process. And supporting all of that with quality systems that allow us to show full compliance with the legislative and regular standards that apply. So I will go now through to giving you a bit of an overview and summary of the work on characterizing at the genome level medicinal cannabis. As I indicated, the starting point was there were a couple of poor quality draft genome sequences, a log of improvement. So what we've done is a very comprehensive pangenome sequence analysis. And so by pangenome, I mean sequencing the genomes of a globally very diverse reference population that we established. And it does give you a sense of diversity groups here. In blue, you have strains that will produce a cannabidiol and tetrahydrocannabinol, so CBD and THC, and with more balanced ratios. Here, a cluster of strains that and genetics and that are high cannabidiol or high CBD producing strains, and a different clustering of a high THC producing strains. So in total, we've sequenced over 690 cannabis genomes, representing a very diverse GenPlus resource. And we also characterized all the proprietary strains that we bred and developed. This is well over 200. And the consequence of being able to undertake that very large-scale genome sequence analysis was that we could identify over 51 million of single nucleotide polymorphisms, or SNPs, or SNPs for short, across the pangenome. And we were able to be validated over 1.7 million high-quality SNPs in the cannabis genome as molecular markers. And that was very important because it provided us the genomic resources required in order to be able to do genomic selection as well as genome editing, and importantly also setting the basis for developing diagnostics or strain-specific marker panels for compliance and stewardship purposes, as well as really understanding structural variations across genomes. And that was, as you see here, you see across different categories of variants. There's a variants that will be between 50 and 500 base pairs long, or between 500 and 10 kb, and from insertion, so in or deletion, so indels. Then we see cases of repeat expansions or repeat a contraction, and as well as time repeat. So understanding a chromosomal and genome architecture across a globally very diverse reference population. And that was critical in order to set the basis for the development of these sinus strains. And the focus was to do so in a genomically selected. And the rationale was that we felt that it would be important to have the ability to, in the future, to develop strains from a paradigm that was, from a recreational use in the past, in an illegal context, into one that is highly responsive to patients' needs and market needs. So believe a mindset of understanding that there will be a very short lifespan of novel strains. There will be a rapid turnover. So being able to do accelerated precision breeding through combinations of genomic selection and genome editing, and the focus on elite strains that are targeted to produce specific compounds and matching extraction protocols and compound isolation procedures to provide efficiencies across the value chain, doing genome edits that enable also novel chemistries, and as well as enabling a rapid integration into elite production backgrounds from a yield perspective, and importantly driving lower cost of production, so that will enable a greater market access and ultimately provide a larger benefit in public health outcomes. So overall, we spent some time in doing a very large-scale plant genome sequence analysis with over 660 cannabis whole genomes sequenced. So possibly very, I would think, an important contribution to advancing the genomic resources development for medicinal cannabis. And so we established the most comprehensive reference genome sequence of one of our strains that we developed, is G.E.T. strain, and that basically contains more than 15% more assembled base than any other genome sequence. So and we published that, and we released that information to advance genomics in medicinal cannabis moving forward. And if you use some benchmark gene sets for reference genome completeness, as you can see here, and the G.E.T. strain outperforms any other genome sequence and contains more than 95% of all genes, is between 3 and 10% more than all other genome sequences developed, which far more complete gene sequences. And you see the sequence names for each of the 10 chromosomes, and the chromosome 6, the large, and X chromosome, and then we've importantly also did a pretty complete genome annotation and developed a genome browser that we host locally, and I will show you examples of how we're using that. So a very comprehensive reference genome sequence and a very complete genome annotation, and paving the way for best of class, I would argue, genomic resources in medicinal cannabis that was genomically say an orphan crop. At the time before we commence our work. So we have an improved reference genome sequence assembled of that Compile 2 strain. We have also done 2 additional reference genome sequences of a very high CBD strain, and also wanted to address the lack of information about the Y chromosome. So we sequenced very comprehensively a male plant. And we combined all this combined genome sequences with all other available genome sequences. And in doing so, actually, we identified 70 megabase pairs of supplemented genome sequence in addition to the combined 2 reference genome sequence. And so here you see some of the statistics of quality of genome sequencing. The other element was to better understand genome architecture and addressing the issues of chromosome nomenclature. And I guess we were seeing some initial publications where people were referring to chromosome numbering that was not congruent between one publication and the other. And so we decided to inform internationally agreed chromosome nomenclature, and did so through with a lens in a rational basis from a comparative genomics approach to related species. So here you'll see and used fig and rows to inform that. So that provided us then a good basis for gene nomenclature and also notations being informed through a comparative gene space analysis. The other important part was to be able to do in supporting and setting the basis for predictive breeding. And as I mentioned, we had developed a genome browser building on that very improved reference genome sequences and a large-scale pangenome analysis. So we've done a pangenome gene space analysis that was enabled through that, and also enabling a detailed characterization of gene presence and absence. And I was making a reference earlier in a previous slide about diversity of insertions and deletions, and using that in a way to predict the chemotype that based on that, I'm illustrating here in this a screenshot of from the genome browser related to a low CBC or kind of a chromin producing strain and a high CBC producing strain. You can see that the low CBC producing strain and basically lacks has a deletion in the corresponding kind of a chromin acid synthase gene. So being able then using genomics to inform to predict chemotypes, but importantly also to enable a target identification for doing genome editing. And so, for example, if we have a breeder strain that is a very high yielding one, but we want to reduce a CBC, we know which tools for doing gene editing we need to do in order to trigger a deletion in that target gene. And so the pangenome gene space analysis was very important then to set the basis for chemotype prediction, and importantly also for target identification for genome editing. So this was just to give a bit of a sense of the work at the genome level, and importantly, we wanted to also inform to look at the transcriptome. And so we've done a very comprehensive transcriptome analysis and gene expression atlases, and using RNA-seq for a diversity of plant organs and tissue types and actually almost cell types, and looking to also how that transcriptome in the key target organ in floral buds doing floral development across 4 different developmental stages, as you see here illustrated in this panel. So, and we apply that to strains that were contrasting strains. So we have a female plant or a male genotype, and also with different chemotypes. So the idea was to have a very comprehensive analysis of how gene expression occurs in medicinal cannabis. So we generated over 70 RNA-seq libraries. We produced close to 7 billion sequence reads. And allowed us then to identify close to 64,727 transcripts as the total number of transcripts, in understanding how they are differentially expressed, these genes across different plant organs and developmental stages. So you see here examples of a heat map. This, for example, is looking at each of the slides here correspond to a different gene, and you will see in red that are upregulated, or in blue downregulated, and so we see classes of genes that will be practically expressed in a female flower, and they will be downregulated in the shoots, or in not in the downregulated in the male flower. Here you see roots, and importantly, we also wanted to focus on understanding gene expression, the transcriptome during trichome development. You see here the scanning electron micrograph on the right, the glandular trichome of medicinal cannabis that is a key type, cell type, and in the context of the key or the main target production organ in floral buds. And so you will see that we looked at specifically sequencing RNA during trichome development from enriched or extracted trichomes, and that across 4 different stages of flower development, floral bud development. And that allows us then to characterize identify the number of transcripts for the key pathways, the biosynthetic pathways in the precursor, both for cannabinoids and as well as for terpenes and terpenoids. So a very comprehensive transcriptome analysis and gene expression atlas across a diversity of tissues, plant organs, and developmental stages, with that allow us then basically to understand the diversity of genes encoding cannabinoid and terpene synthesis across strains. I'll move now. So that was to give you a sense from a genome to. So I'll reduce the volume of this. So from genome to transcriptome, and now moving into understanding the trichome metabolome and also the volatilome, the volatiles. And so we put to the battery of technologies that we have in place, and such as ultra high performance chromatography with a photodiode array detection, and enabling quantitation and detailed analysis of cannabinoids, and as well as related metabolites, applications of liquid chromatography mass spectrometry to support that, gas chromatography mass spectrometry, and as you see also here in this video, using the ability to sample the headspace so that we can look at volatiles and doing a direct injection in GCMS and for volatilomics, and then the structural elucidation of novel cannabinoids, and as well as rapid profiling of plant extracts using NMR, nuclear magnetic resonance spectroscopy. This is our NMR facility that we have in AgriBio, and done that for a diversity of strains in a very comprehensive manner, so that we can really understand the metabolome and volatilome, and noting we were interested to really understand the volatile components that, as you know, are responsible for the aroma difference between strains, and importantly, some are also bioactive and believe them to contribute to the entourage effect. And I will describe a little bit of this in a minute. The metabolome analysis comprised the profiling that brought chemical diversity, and you see then a range of strains that we bred for each of the different cannabinoids. And we done chemotype profiling across a range of developmental stages, and a very comprehensive chemotyping of the very diverse reference population, and also a chemotyping for the major volatiles. So exploring the totality of the chemical diversity of cannabinoids and terpenes in the cannabis reference population. And all these methods, we also looked at validating all the methods, and here describe the example for rapid and low-cost approaches and methods development for targeted quantitation and of cannabinoids, and publishing those and using that also to inform the GMP, the good manufacturing practice processes for the manufacture of it. We've done targeted quantitation using mass spectrometry, and saw 16 commercially available compounds and of major aminocannabinoids, and we did structural a confirmation of those using our NMR facilities to ensure that the quantitation protocols are very robust. And then using that, for example, here you'll see cannabidiolic acids, or CBDA, or tetrahydrocannabinol, or CBC, or CBN, and CBD. So being able to give the other examples for THCV or CBL and CBG. So a well-established and robust methodologies for targeted quantitation. And then apply that. Here, see for two very contrasting strains. This is our Cambio 1 strain, and this is our Cambio 60 strain. So you will see the very diverse chemotype of these strains, and so using quantitation for targeted strain selection. And here's the examples of there's 16 different cannabinoids, and for the diversity of strains that we bred over a period of time. And you'll see this includes obviously the levels of CBD and THC. And but then if you remove those and look at the aminocannabinoids, the corresponding chemotypic diversity of the strains selected, and that allows us to identify basically 4 distinct clusters, informed by a clustering analysis taking those major and minor cannabinoids. And importantly, we looked at across the different developmental stages of flower development at the harvest time, so that we can create data that reflect the metabolome analysis linked and congruent with the transcriptome analysis that I showed you earlier. So we see that there's here representing a 5-week harvest periods for different harvest times, and you'll see how changes in the metabolome occur related to major and minor cannabinoids. So overall, the cannabinoid content changes over 5 weeks. We characterize for a wide range of proprietary strains, so then we find that the variation is consistent across strains, but their individual cannabinoid concentrations are strain dependent, and the harvest time will be dependent on the desired cannabinoid profile. So at the same time informing cultivation and harvesting practices for quality and consistent through the year supply of manufactured or extracted medicinal cannabis. So in a form using a specific harvest time for the treatment, aligned with the treatment of specific medical conditions. Summarizing the metabolome analysis side, again, we did targeted quantitation to determine the expression levels of the known targets. We look at 16 commercial available compounds of cannabinoids and major and minor ones. 14 of those we determined using mass spectrometry, and 2 of those we determined using UV visible spectroscopy. And we developed a fully validated and published method for the quantitative analysis of cannabinoids. And we have a catalog of over 200 individual strains that we have quantitatively chemotyped for cannabinoid content. And then also a targeted and untargeted statistical analysis to understand clustering, chemotypic clusters of those, as well as implications of harvest periods for the cannabinoid composition. As I mentioned, we were interested also to understanding the volatiles, the volatilome, as part of the metabolome analysis. And so these, as you know, these are terpenes and terpenoids. They are a very structurally diverse class of C5 to C40 hydrocarbons. They're built on as the primary unit being isoprene as a C5 one, and they are produced by various organisms for a variety of functions. And in cannabis particularly, they're dealing with monoterpenes that are basically C10, so 2 units of isoprene with side or group, a variety of functional groups, and sesquiterpenes that are C15. As I indicated, they are basically volatile monoterpenes that are C10 and semi-volatile sesquiterpenes that are C15, and again a significant chemotypic diversity and terpenes. And importantly, I wanted to understand, as you know, they are common biosynthetic precursors for the synthesis of both terpenes and cannabinoids, starting with dimethyl paraphosphate and isopentenyl paraphosphate, leading then to the production of the phytocannabinoid acids and acidic forms that then are decarboxylated and produce the active, let's say, phytocannabinoids. But then this one can be then linked into with a loss of paraphosphate into the monoterpenes such as myrcene, or with starting with the farnesyl paraphosphate and the building then the C15, the sesquiterpenes. And most of these compounds have individually attributed or recognized biological activities. They are present at pharmacologically relevant concentrations. They have are very highly bioavailable, and as you know, they will interact with cell membranes and proteins such as G protein coupled receptors or P450s, and importantly, also they modulate the response to the major cannabinoids, the psychoactive tetraendocannabinol and the non-psychoactive cannabidiol CBD, which is the concept of the entourage effect that we wanted to better understand, or set the basis to better understanding it. So that provided us a basis of doing a very comprehensive correlation map of all this chemotypic or metabolome diversity, quantitating 16 different major amino-cannabinoids, and as well as a 42 or 43 terpenes, and this gives you a sense of that. Sorry, I'm taking too much of your time, but I will maybe rush it through to telling you the bit of how we developed a basis for a precision and genomically assisted breeding. As you know, with key drivers, so being clear about what is the design and is a cannabis plant, and obviously economics plays an important role. And if we want to build an industry, we decided in Australia that is with high quality standards, and obviously the focus is on indoors cultivation facilities or greenhouses rather than broad acre ones, and that comes with a cost structure, as you can see here, that makes breeding targets critically important. And so breeding for strains that would be fast growing, that has a time to maturity. The precocity is important, the time to maturation, that are robust and stable, they're highly productive, and they produce a commercial size product in a consistent manner. They have a high harvest index and needless distress, the desired and a cannabinoid profile. Key components of yield, needless distress, are the batch dry weight, and you'll see here a frequency diversity of those, very broad ranging, as well as days to maturation. And so being able to, in indoors facilities, to doing up to 6 cultivation cycles per year, and that is a noting. These are give you a bit of a sense of prices of cannabis, and will range between $6 and $13 per gram. And so understanding yield components was a key element that we wanted to drive. So the breeding system that we use, the breeding methodology that we use, was accelerated breeding through genomic selection, and basically what we have is a reference population which is very diverse. We have genotypic data and phenotypes, so it's very comprehensively characterized, and I went through that already in the previous slides. Then developing a prediction equation that describes genome-wide the contribution of every single nucleotide polymorphism of every SNP to the relevant trait, and then we can apply that genomic prediction to selection candidates, so we can do targeted crosses. And then at very early stages, just in the first leaves, sampling those, obtaining DNA, creating a genotype, and based on that, being able to do the selection of parents for the further a crossing cycle. So genomic selection is obviously very useful for traits where the variation is contributed by a large number of loci, and that's obviously the case for the key traits that I described before. Is particularly provides a large benefit for traits that are very difficult or expensive to measure, or are measured late in the breeding cycle, and needless distress that in medicinal and cannabis chemical composition is critical. It happens at the flowering stage of the floral bud as the target plant organ, and so very late in the cycle. And the use of genomic selection in breeding medicine and cannabis is the path that we pursued, and is and meets, I think, ideally is an ideal target for that, and allows them to accelerate genetic gain, because allow us to reduce the generation interval, and importantly also allow us to increase the accuracy and the intensity of selection. So the journey that we took was then rather transitioning from out of conventional plant breeding into what we call genomic breeding 3, which enables then a large-scale crossing to be very effectively used and very efficiently screened through genomic selection. Very important, because for us, as I indicated, on the cost structure of growing indoors in an indoors facility, medicinal cannabis is very high, and in order to be able to optimize population sizes, we also moved into did a computational design of the optimal crossing, so a program for that to realize the maximum genetic gains. So transitioning from incremental improvements, and that is what historically has happened, and most of that possibly happened in the past decades in an illegal context, into a genomic breeding where we genotype the seedlings. We computationally design the best crossing of the best genetics. We're going to take only those best crosses, and we only trial lead plants for the new strains, and otherwise we tend to screen the offspring from the desired families. And so cycling very fast, Importantly, obviously, and I move now into the latter part on phenome analysis, is developing all the tools for phenomics to support that accelerated breeding. And so we developed indoors 3D LiDAR mapping, and you have seen this image here that allow us basically to phenotype indoors. Has an accuracy of 2 millimeters, so it allows us then to very rapidly measure traits, growth rates, and strain performance, and also doing rapid non-destructive cannabinoid phenotyping using a handheld micro NIR that we have validated for 65 strains, which has an excellent prediction, particularly of THC and CBD, well, the acidic forms, THCA and CBDA. And so that we validated in order to be able to do very fast and quick. So basically in half a second, we can do the measurements, and it is well correlated. So we've developed initially for 5 of our AgriBio strains. We validated with 65 additional ones. And so we have a rapid methodology for chemotyping now. I mentioned the importance of yield components, and we went we did a comprehensive weekly phenotyping of the reference population, measuring, I think, 12 different vegetative state type of traits, and I think 16 ones relating to the key target organ, floral buds. So really understanding using digital phenotyping of floral buds to optimize what are the optimal yield dimensions for floral traits. And we were able to reveal the very significant variation for all the traits. We were able to identify that, and that provide us also insights into the physiology of cannabis biology and the traits, associated traits, so that we can look at which identifying correlated traits that assist us with the definition of breeding targets and developing then, say, breeding or selection indices that will predict at the vegetative stage and the final performance. As you see here, the transition then after 3 weeks from planting from the long day to the short day for flower induction in a range of diversity for the range of phenotypic yield components. And we've done the corresponding analysis related to a major and cannabinoids and total cannabinoids, so looking at cannabinoid data and the respective reflective in cannabinoid content and composition. Very briefly, and I finish in a couple of minutes, I wanted to set the basis for genome editing to be able to, in a very targeted manner, to create mutations. And we need to obviously establish all the methodologies and capabilities to do so. So the tools for genome editing, the example I'm showing you here is using synthetic nucleases. The targeted focus was for our side doing targeted deletions. And it takes us back to the point of having done the comprehensive genome and transcriptome analysis to enable target definition for this type of work. But again, there was a paucity in availability of the methods in order to be able to, in tissue culture, in order to be able to deliver these tools for genome editing in target cells and being able then to recover gene edited or transgenic as an alternative opportunity. So all our strains, we've established robust protocols for maintaining those in vitro culture. So here are examples of that. We wanted to establish also methods for maintaining strains not only in vitro, but allow us to very rapidly and clonally propagate strain multiplication. And we did that via the use of artificial seeds. So we take axillary buds that we coat with calcium alginate, and we produce artificial seeds. Let's say they can then be stored in a cold room, and then they are easily can say germinators, artificial seeds, established shoots, and established plants. We develop protoplast isolation systems and in order to be able to test the efficacy of vectors in stem finger nucleases for target genes that using transient assays, and to establish all the methods for in vitro culture. So this is colors, production, differentiation of shoots, rooting of those, and rooting of established shoots and plants. So all the methodologies in order to be able to do targeted genome interventions and using either transgenesis or gene editing. And then complementing their work, this is now introducing the concept of designing strains. So once I have a collection of proprietary strains and one wants to create targeting mutations to optimize certain yield components, I indicated that the genome and transcriptome analysis allowed us to identify every gene involved in the biosynthesis of cannabinoids. Then we designed guide RNAs to do CRISPR-Cas9 and gene editing, as well as stem finger nucleases for every gene, and designed those in a form that allow us to have universal guides so that we can really, for example, block a complete step in the biosynthesis, but also some that are very unique, noting that we have multiple gene variants and revealed by the transcriptome and comprehensive pangenome analysis. So all the tools for the development of designer medicinal cannabis strains through gene editing, we have all those developed, as well as the methods in order to enable that to happen. And finishing now, the last stages related to supporting the industry development moving forward. We developed the plans of those understanding. We did the industry development modeling, and then our substantive role on undertaking collaborative research and development and licensing of strains under a brand that we called CAMBio by Agriculture Victoria Services, the commercialization arm of Agriculture Victoria Research, and through an entity or a platform that we call CAMBio. And so it's indicated as to intellectual property outputs. We secured Australia's first proprietor's rights for 3 proprietary medicinal cannabis strains. And we have developed a range of technologies and tools in medicinal cannabis systems biology, which is the second part of the seminar that they give today. And we filed, basically, we have all of those technologies and tools patent protected and a trademark to support the commercialization of those. And in more recent time, we post the filing of the provisional patent applications. We are now catching up with peer-reviewed publications that and here's a subset of that from Genome to Phenome. So summarizing the second part of the talk related to technologies, tools, and science outputs and deliverables, we sequenced over 690 cannabis genomes. We established, I think, a very large genomic resources for comprehensive genome sequence assembly. We discovered and validated over 1.7 million DNA markers for accelerated breeding via genomic selection. We developed a panel of 50,000 molecular markers for very low-cost implementation of genomic selection. We developed and characterized over 275 proprietary strains with a very wide range of chemotypic profiles, and we have a seed bank of thousands of seeds as a germplasm resource for ongoing accelerated precision breeding, including 42 new high CBD strains that we are further evaluating now. We establish all the methods for the generation of stem cells in cannabis, enabling the recovery of whole plants from single cells for the first time, and that provides the ability to undertake precision breeding of designer strains via gene editing. And in addition, I didn't have time today to cover, we identified and characterized novel microbial strains for the development of microbial products with biofertilizer, bioprotectant, biostimulant properties for low input organic indoors cultivars. So concluding, and I feel that the medicinal cannabis industry will benefit from advances in plant systems biology. We have genomics tools and resources established to enable diagnostics for traceability and enforcement and accelerated breeding through genomic selection. They've established a capability to enable targeted genome editing for the production of novel designer strains. We've done very comprehensive trichomes characterization from transcriptome through to a metabolome, and including volatilome, and taken across a wide range of germplasm, a very comprehensive metabolome and volatilome analysis, again across a wide range of germplasm, and established that CanBio platform for accelerated precision breeding. And I'd like to finish by acknowledging the wonderful team of people that were behind this work. So thank you very much again for your attention. Apologies that have taken too much of your time. And I think I'm trying now to cease sharing, and I'm happy to answer any question. Thank you.
Bueno, los infinitamente agradecidos somos nosotros, y además estamos apabullados con tanta experiencia y tanto desarrollo, bueno, en fin, que tienen ustedes allá. Así que muchísimas gracias por preparar esta presentación, por tomarse el tiempo de exponerla ante nosotros, por compartir sus conocimientos. Y bueno, permitimos que tome un breve descanso, que tome un vasito de agua, doctor Spangenberg, si, si quiere, para reponerse un poquito. Y tenemos algunas preguntas para hacer. ¿Podemos empezar?
Excelente. Sí, claro que sí.
Bueno, es posible, si bien hemos estado procesando durante la charla las preguntas que iban surgiendo, capaz que algo de lo que le preguntamos ya lo dijo y no alcanzamos a borrarlo de la lista. En ese caso, bueno, nada, nos dice que ya esto ha sido explicado. Una de las primeras preguntas que nos han planteado es ¿por qué desde un inicio utilizaron hidroponía?
Bueno, el objetivo era evitar contaminación, digamos, para los efectos de asegurar que tenemos good manufacturing practice, estándares de producción que son compatibles con los requerimientos de GMP. Queríamos evitar tener que trabajar con suelo y otros sustratos. Entonces, y poder controlar mejor el suministro de nutrientes.
Muy bien. Otra pregunta. ¿Encontraron una buena correlación en las mediciones de cannabinoides realizadas por espectroscopía de infrarrojo cercano y HPLC? Cromatografía líquida de alto desempeño.
Sí, digamos, lo caracterizamos, hicimos el análisis comparativo, tenemos buenas correlaciones, validamos la metodología para, creo, unas 65 strains, así que para THC y CBD damos confianza en la metodología, y que es el primer pass de chemotípico, de screening chemotípico para selección, pero lo hace mucho para apoyar un programa de mejoramiento. Es una herramienta muy útil.
Muy bien. ¿El micro-NIR se usa solamente para cannabinoides?
Sí, lo tenemos, bueno, lo hemos validado solamente para cannabinoides. Y fundamentalmente, como decía, con foco en CBD y THC.
Una pregunta un poco difícil, pero bueno, un dato muy general. ¿Qué presupuesto debieron destinar para todo el trabajo realizado? Nos preguntan. Y bueno, una aproximación.
Bueno, en la primera fase que teníamos, por supuesto, tuvimos que establecer toda la infraestructura y pusimos más o menos unos $5 millones, o $1 millón por año durante 5 años, desde el 2014 hasta el 2018. Pero eso incluye todos los costos de infraestructura, ¿no? ¿Verdad? Tuvimos que establecer una indoors cultivation facility, lo mismo de manufacture, para hacer, manufacturar productos de cannabis medicinal. So, incluye costos de infraestructura.
Bien. Otra pregunta. ¿La producción de líneas de germoplasma están a cargo del gobierno solamente?
Bueno, el programa nuestro fue de gobierno hecho. Ahora tenemos un sector privado en los cuales le damos servicios, hacemos el mejoramiento para ellos, digamos, ¿no? Pero está financiado por el sector privado y nosotros tenemos los recursos genéticos y las metodologías, ¿no? ¿Verdad? Así que proveemos al sector privado de los servicios de mejoramiento. Así que sí, el gobierno lo hace, pero esta parte paga por el sector privado.
Ajá, bien. Otra pregunta. ¿Qué tipo de materiales desarrollaron? En este sentido, ¿desarrollaron líneas puras e híbridos, poblaciones de polinización abierta, clones con cierto grado de heterocigosis?
Lo que hacemos es básicamente, quizás lo conté un poco muy rápido al final, nos enfocamos en desarrollar strains que son luego propagadas en forma clonal. Así que hacemos cruzamientos, hacemos el genotipeado, y aplicamos ecuaciones de predicción de selección genómica, de modo que hacemos un screening muy con alta intensidad de selección, y luego solamente llevamos a floración los fenotipos que podemos predecir en base a selección genómica, que son los mejores candidatos. Los confirmamos con las características del genotipo, y usamos eso como nuevos padres, ¿no? Así que esa diapositiva que mostré con el esquema de selección genómica es lo que aplicamos. Y lo que hacemos es, en forma computacional, determinamos cuáles son los mejores padres para cruzar.
Bien.
Pero está todo diseñado para desarrollar strains de que luego van a ser propagadas en forma clonal.
Muy bien. Otra pregunta. ¿Han desarrollado o tienen como objetivo desarrollar patrones heteróticos en cannabis para la producción de híbridos?
No estamos trabajando en eso.
Muy bien. Una pregunta que es muy del momento con el mundo de las criptomonedas. ¿Han considerado implementar la tecnología blockchain para la trazabilidad de los procesos?
Sí. Y tenemos trabajo encaminado en ese área.
¿Sí?
Sí. Y tenemos un sistema que lo estamos piloteando ahora para también ligarlo con digamos, información, entender, a los efectos de entender y hacerlo de la disección del efecto de entourage. Tenemos que, en forma segura, digamos, conectar datos de la planta con performance del producto o reacción de un paciente. Y hacer ese diálogo extremadamente seguro. Así que estamos utilizando el sistema del gobierno de Victoria, que en comienzo fue establecido con el propósito de violencia doméstica. La verdad que tenemos que conectar datos que el gobierno tiene distintos departamentos, desde policía hasta el departamento de justicia, etc. Así que estamos usando ese sistema para establecer conexión entre genética de la planta con respuesta a nivel de pacientes en una forma que es segura.
Bien. Otra pregunta. Bueno, esto puede ser un poco largo de responder. ¿Cuál es la composición de la solución nutritiva para hidroponía en las distintas etapas fenológicas?
No tenemos esas recetas y está todo eso, parte de las nuestras Standard Operating Procedures. Lo puedo compartirlo eso luego, Cecilia.
Bien,
Sí,
bien, bien.
que me escriban.
Sí, sería muy largo de responder. Otra pregunta. ¿Tienen machos en sus programas de mejoramiento o se valen de técnicas de androgenización de hembras para los cruzamientos?
Ambos métodos, pero en la fase que estamos ahora hacemos androgenización de hembras.
¿Hacen androgenización?
Sí, pero tenemos también, trabajamos con ambos métodos, ¿no es verdad?
Con ambos métodos. ¿Y para androgenización, qué procedimiento usan predominantemente o usan varios según el material y según el caso?
Te puedo mandar también el protocolo de eso, ¿no es verdad? Creo que está bastante bien establecido.
Muy bien. Bueno, otra pregunta. ¿Cuál es la dificultad que impidió hasta ahora caracterizar el cromosoma Y, el cromosoma sexual Y? ¿Desarrollaron marcadores moleculares para sexar plantas?
Bueno, digamos, durante mucho tiempo no lo habían, digamos, las primeras secuenciaciones se hicieron con plantas hembras, ¿no? ¿Verdad? Es el genotipo productivo. Nosotros queríamos mejorar los métodos diagnósticos molecular para sexaje de plantas. Al principio usamos para las primeras métodos que están publicados. Y ahora sí tenemos marcadores excelentes porque tenemos toda la secuencia completa del cromosoma G.
Muy bien. Otra pregunta. ¿Hay marcadores económicos que no requieran secuenciación para determinar el quimiotipo a partir de la caracterización de variantes de THCA y CBDA sintasa?
Sí, hay algunos diagnósticos de que no son muy precisos. Así que yo recomiendo hacer secuenciación, ¿verdad? Y los costos de secuenciación en el momento están relativamente bajos, ¿no? En forma comparativa, creo que la tecnología de secuenciación ha llegado a una estructura de costo clase competitiva. Tenemos un panel de unos 50.000 SNPs para implementar selección genómica en forma muy efectiva, incluyendo marcadores para el perfil chemotípico.
Muy bien. Nos quedan dos preguntas nada más. Una de ellas. ¿En la obtención de qué cannabinoides se centró el trabajo de ustedes? Bueno, creo que en varios. ¿Y qué cantidad de biomasa, por ejemplo, cuántas toneladas se necesitan para obtener una cantidad significativa para la población de algún cannabinoide?
No sé si entendí la pregunta. ¿Son los métodos que usamos para quimotipeado? ¿Es esa la pregunta?
No, la primera parte de la pregunta es ¿en qué cannabinoides se centraba su investigación? ¿En la obtención de qué cannabinoides se centraba su investigación? Creo que de varios,
Sí.
pero...
Sí. Bueno, digamos, la necesidad del mercado cambia, ¿no es verdad? El enfoque que tenemos ahora es más diseñar strains con enfoque en los minor cannabinoids. ¿Yeah? Fundamentalmente hay CBC, cannabicromine, CBN, cannabinol y CBG, cannabigerolic acid. Esos son tres muy importantes.
Y una idea aproximada, ¿qué cantidad de biomasa es necesaria para obtener una cantidad significativa de alguno de estos cannabinoides?
No estamos involucrados además en la parte de manufactura,
Bien.
pero no puedo darte. Sí.
Hace falta mucho.
Sí.
Bien. Última pregunta. ¿Se conocen las causas genéticas o moleculares del hermafroditismo? ¿Se puede controlar este carácter en un programa de mejoramiento?
Estamos interesados en ese área, no tenemos las respuestas para eso, pero es algo que queremos entender mejor.
Bien, sí, nos preocupa a todos.
Muy buena pregunta.
Bueno, no tenemos más preguntas por ahora, doctor Spangenberg. Le agradecemos muchísimo todo este tiempo que ha dedicado, todo el esfuerzo. Sabemos que hace tantos años que se comunica en inglés que, en fin, ha sido más conveniente presentar en inglés y bueno, y está esforzándose bastante en esta parte de las preguntas para entendernos y para que podamos entender este tramo final de las preguntas y respuestas. Así que bueno, allá es la mañana, después de este gran esfuerzo tendrá que irse a trabajar, así que lo liberamos. Nuevamente muchísimas gracias.
Muchas gracias, Cecilia, gracias a todas y todos y que tengan una buenas noches.
Bueno, muchas gracias y un excelente día por allá.
Gracias, hasta luego.
Hasta bien prontito.
Gracias, Gustavo. Chaucito.
Chao.